Okay, so in our last video we were talking about finding the cubic model for this data set of, let me go back to the data set to remind you. We had this data set of population from 1900 to 1990, population in millions of the western US, and we looked at several different models and decided that actually the cubic was the best one to use. Given that the quartic has turning points, which kind of, even though the quartic model fits better in terms of the coefficient of determination in the SSE, the cubic is better because it doesn't have any kind of radical changes in its behavior. Okay, so let's talk some more about the cubic model. First of all, let's discuss the model's average error in relative terms. That means let's look at the average error in relation to 1900 and 1990, kind of in the extremes of the data set. So we'll do that first. So the average error, now remember we calculate the SSE, and then the average error is the square root of the SSE over 10 in this case, because 10 is the number of data points that we have. And that would come out to be 0.72 million. Okay. Now, in terms of the 1900 population, which was 4.309, so we're going to calculate sort of like the model or the percent error, but for the average error. So remember, the percent error is the model error divided by the actual times 100. So that's essentially what we're doing here, except with the average error. And so on the 1900 population, this accounts for 16.7% of the data. If we zoom over to the other end of the data set, the 1990 value is 52.786 million, and calculate the average error, relative average error there. That's only 1.4% of the 1990 population. Okay. We're not really going to do much with these average error computations, but yeah, there they are anyway. Part B, what can you conclude about the fit from the model's correlation coefficient? Well, it doesn't have one. It doesn't have a correlation coefficient. So, can't really conclude anything from that. So let's move on to C. What can you conclude about the fit from the model's coefficient of determination? Okay, the coefficient of determination was found to be 0.9979. Remember, that was r squared. Now, if we convert this to percent form, we get 99.79%. And remember, what that means is that this explains this percent of the variation in the data is explained by the model. So 99.79% of the changes we see in the actual values is the independent variable changes. It is explained by the model. So that's good. That is good. Okay. Using the cubic model, let's use this model for a few things. Namely, let's calculate the population of the western US in 2000. Let's do that first. I think I still have this. Let me see. Actually, that's the quadratic. Let me calculate the cubic model. Okay, and then I want to calculate the population in 2000. So that's going to be 2000 minus 1900, so that's 100. So it's 64.54 or 55 million. Now, if the actual population of the western US was 62.19 million, calculate the model error and the percent error. Well, model error is actual minus predicted. So that's 62.19 minus the answer we just got. That's our model error, negative 2.35, and then divided by 62.19 times 100, and there's our percent error, 3.79%. So that's relatively small, not bad. Here's those computations again. And I guess the last question is, what can we say about the goodness of the model's prediction? Well, if we have a I forgot what it was, 3.79% error, that's smaller than 5%. And so that's a pretty good fit. Yeah. Okay. Let's look at another example. Here's a table of data. The above table was obtained from one of the following function types: linear, exponential, logarithmic, quadratic, cubic, or quartic. What kind of function is f? Write f with coefficients rounded to 5 decimal places, and then do some stuff with the function. So let's input this data. I'm going to input this data off camera in my lists, and then we'll talk about graphing it. Okay, so I've entered the data off camera, and what I'm going to do first is I'm going to delete this function, but I'm going to do a stat plot just to see if I can rule anything out and pick any likely candidates for what type of model would be best here. So let's go to Zoom, and we want to do Zoom stat. Okay, so we can actually rule out quite a bit with this, because this is decreasing at an increasing rate. So, it's doing that. And that actually rules out a lot. That rules out logarithmic, that rules out linear, that rules out exponential, that leaves in our polynomial models. Okay, so we really have to check all of them, because a quadratic can do this, a cubic can do that, a quartic can do that. So they can all do this over certain portions. Now, how do we pick which one is the best, right? So I guess what we'll do is we'll start off with quadratic, and as this slide discusses, the method that we're going to use for this is the following. We'll start with the smallest n, which would be 2 for quadratic, and how we will know when we have a good fit is when the data values are reported to 2 decimal places. Since our data values are reported to 2 decimal places, when our average error is no longer significant to that level, we will know that we're there. Okay. So in other words, we'll need to actually calculate the average error and see if it has zeros in the first 2 decimal places, and then we'll be good. All right, so let's do quadratic. And I'm going to immediately calculate the SSE. And I'm going to immediately calculate the average error. I don't know how many data points we had, though. 1, 2, 3, 4, 5, 6. Okay, 6 data points. All right, so this is too big. We still have significant digits in the 10th place. So let's go to cubic and see what we get with that. Forgot my parentheses again. All right, calculate the SSE. Okay, this is looking good. Now let's go to the average error. I say it's looking good because it's small, so okay, perfect. That's great. So that's exactly what we want. We want to have zeros in the 100th and the 10th place, and that's what we have. So this is close enough. So we're going to go with a cubic regression for this. So we will use cubic regression. Oh, and I guess we have other questions to answer, don't we? All right, so we've decided it's cubic, and I guess we just found f. We found our coefficients. If you actually wanted to report this on in the test, you'd have to go through here and round each of these to 5 decimal places, and be careful because it's a lot of numbers to deal with. But now to find f of 9, okay, no problem. That's just evaluating the function, right? So we go to vars, yvars, function y1 of 9, and that's our value, 18.33. Solve f of x equal 50. Okay, that is a calc intersect question. So I'll go and enter y2 equal to 50. And let's look at our window. Actually, let's look at our table. Okay, so between 7 and 8, we cross 50. So we can just do maybe 0 to 10. So now we'll do the calc intersect procedure. And we get f of x equals 50 when x equals 7.66. All right. So I think from here we have a few more questions to answer about this. So let's go to those. Oh, and I'm wrong, actually, that's it. That's all our questions for that one. I think we've got one last example to take a look at. And I will do this in the next video.